We have studied scalar fields, which had the Lagrangian for the real scalar fields, squared minus m squared over 2 phi squared, and they satisfy the Klein-Gordon equation. We had also seen the Schrödinger field, which if you just write it in this form, this basically satisfies the Schrödinger equation. Where in this case the Hamiltonian is can be written as p squared over 2m plus v of r. Now the Klein-Gordon field is essentially this is basically the relativistic generalization of the Schrödinger equation. You see, the Schrödinger equation tells us that if energy of the particle for a free particle is p squared over 2m, which is just a non-relativistic energy momentum relation. If you search for free fields for the Klein-Gordon equation, their energy momentum relation is given by, for the Klein-Gordon field, their energy squared is equal to p squared plus m squared, which is nothing but the relativistic version, relativistic energy momentum relation. But as we go from the Schrödinger equation to Klein-Gordon equation, one problem is that although the Schrödinger equation is first order in time, the Klein-Gordon equation is second order in time. So one can ask the question, is it possible to obtain an equation for a relativistic equation for which the energy, the equation is also first order in time, just like the Schrödinger equation? Well, the answer to this one is the Dirac equation. And let's see how we can get the Dirac equation. So we would like to obtain an equation E of phi for the free field. Here the E is the energy operator. It's just a time derivative operator. Now I will be using the E and P interchangeably, both for the operator and also for the corresponding eigenvalue. And we would like to have this, since it is first order in energy, it has to be also first order in momentum, because relativistic mechanics tells us that energy and momentum, they're just components of a 4 vector, and they have to be symmetrical in our equations. So this should be alpha I pi plus m beta phi. So we are looking for an equation of this form. For the time being, we don't know what these alpha i's and beta are. But if this is satisfied, we also want this equation to be consistent with the relativistic energy momentum relation. So let's look at what this equation tells us for E squared. So E squared phi is equal to E of alpha I pi plus m beta phi, where I used this equation once. But the energy operator is just a time derivative, whereas the momentum operator is position derivative, and they just commute with each other. And similarly, there's alpha I and m, they will be time independent, and hence they commute with the energy operator. So this becomes alpha I pi plus m times beta phi, beta E phi, which is alpha I pi plus m times beta alpha let me use a different dummy label, alpha j pj plus m times beta phi. And we would like this to be p squared plus m squared phi, so that it's at the energy squared is the momentum squared plus the m squared, the relativistic generalization of the energy momentum relation. Now, of course, if this line is equal to this line, let's just multiply out the previous line, this line. If we multiply it out, we will get alpha I alpha j pi pj plus alpha I beta pi times m plus m times alpha I beta pi plus m squared beta phi. Okay, a couple of things I have done. So here I have the product of this term with this term, that is the first term over here. Then I have the product of the first term in the first parenthesis and the second term in the parenthesis, it is this term. And then I have the second term in the first parenthesis and the first term in the second parenthesis. But note that this j is a dummy index, so I just renamed it to I when I'm writing it over here. And then I have the m squared term over here, and this is beta squared. Now, if you compare this line, because we want this line to be equal to this line over here, you see in this line there are no linear terms in pi, so the linear terms in pi appearing here, they should disappear. And that is only possible if alpha I beta plus beta alpha I is equal to 0. Here I made a mistake. This term is this times this one, so beta comes first. So beta alpha I. Okay, so just anticipating the result, I'm just keeping the positions of these alpha and beta factors intact. So I obtain such an equation for alpha I and beta I. Now this equation already tells me that alpha I and beta are not numbers. So if they were numbers, they couldn't satisfy this relation. So they have to be we can represent them by matrices. Now let's continue further here. So this makes sure that these two terms do not appear. And here the m term only appears here, so with the coefficient beta squared. So here m squared has a coefficient 1. So that is what I want also. Beta squared should be equal to 1. Now I already started writing them as matrices because this equation already tells me that beta cannot be just a number. So it's some kind of a matrix whose square is 1. Now we are left with this term and this term. They have to be somehow, this term should somehow be converted into just a p squared. So what we want is alpha I, alpha j, pi, pj to be equal to p squared, which is pi, which can also be written as pi, pj, Kronecker delta ij. So we obtain alpha I, alpha j minus Kronecker delta ij, pi, pj. This is equal to 0. Now, this should be valid for any pi, pj, but one should be a bit careful in this equation. You see, this doesn't imply that this parenthesis over here is 0. We cannot say that this is 0. So what we can do is, one should pay attention to, let's just take any anti-symmetric matrix and some symmetric matrix. Here, what I mean by an anti-symmetric matrix is when you just change their indices, it just acquires a minus sign, and for a symmetric matrix, there's no sign change. Now, if we have such matrices, I and j, if we multiply them, and remember here we are summing over I and j because they are repeated, what we get is this is equal to, well, since we are summing over I and j, they are just dummy indices, so I can just change their name. So I will first rename I to j and j to I. Well, if I do that, I get AJI, SJI. You see here I didn't exchange indices, I just changed the name of the indices. So that is why I don't get any minus signs anywhere. Now I am exchanging the indices. Now I will be exchanging the indices of the anti-symmetric matrix. So it becomes minus Aij. And if I exchange the indices of the symmetric matrix, this is Sij. So this is minus Aij, Sij. So you see that Aij, Sij, this product when summed over the dummy indices, it becomes minus itself. But that basically tells me that Aij, Sij is actually 0. So if we go back to this relation over here, let me write it in a slightly different form. So alpha I, alpha j plus alpha j, alpha I over 2 plus alpha I, alpha j minus alpha j, alpha I over 2 minus Kronecker delta ij times pi pj. This is equal to 0. But you see that this is anti-symmetric in I and j. If I change I and j, this whole thing changes sign, whereas pi pj is symmetric under the exchange of I and j. So when I multiply this term with pi pj, I automatically get 0 independent of the properties of alpha i's and alpha j's. So this tells me that alpha I, alpha j plus alpha j, alpha I over 2 minus Kronecker delta ij pi pj, this is equal to 0. So now this is anti-symmetric. So is this one, this parenthesis. Now I can say that, now this is symmetric, sorry, this pi pj is symmetric. This is symmetric. Now I can say that this is 0. So I know that alpha I, alpha j plus alpha j, alpha I should be equal to twice Kronecker delta ij. So if we sum up, we said that the energy operator should be equal to alpha I pi plus beta m, where alpha I, alpha j anti-commutator is twice Kronecker delta ij. Alpha I beta should be equal to 0, and beta squared is 1. Now note that this equation also tells me that alpha I squared is actually equal to 1. Note that here there's no sum over I. Since I is repeated, unless I specify that there shouldn't be any sum, this would mean alpha I squared summed over I, and that is definitely not 1. So this is basically our first order equation consistent with the relativistic energy momentum relation. Well, the Dirac equation is usually not written in this form. So E is equal to E of phi is equal to alpha I pi plus beta m. And the reason why it's not written in this form is, you see, although it is relativistic, as we will study in more detail later on, and the energy and momentum still doesn't seem to be on equal footing. The momenta are multiplied by some matrices where the E is not multiplied by any matrix. So what we will do is just multiply this whole equation by beta. So beta E minus beta alpha I pi minus m, beta squared is just 1, phi is equal to 0. Now energy and momentum is a 4 vector. It's p mu. So I will define gamma 0 to be beta, gamma I gamma 0 to be beta, gamma I as beta alpha I, so that gamma mu p mu is actually equal to which is gamma 0 p0 plus gamma I pi, which is gamma 0 p0 with the lower indices, which is just beta E minus beta alpha I pi. So here this whole thing becomes gamma mu p mu. Now the combination gamma mu p mu, we will have, it appears quite often, so there is a special notation for this. Whenever you have a 4 vector contracted with a gamma matrix, we will show it by p slash. So now the Dirac equation, this equation over here, becomes p slash minus m phi is equal to 0. Note that since gammas are matrices, and so is phi. Phi is a row matrix. Now let's look at the commutation relations of these gamma mu's. So let's look at gamma 0, gamma I. This is equal to gamma 0 is beta, beta alpha I minus beta, no, plus beta alpha I beta. This is equal to beta squared is 1, so this is alpha I. Beta and alpha I anti-commute, so if I change the position of this alpha I and beta, I get a minus sign, minus beta, beta alpha I, but beta squared is just 1, so this is 0. So gamma, the space component and the time components of these gamma matrices, they anti-commute. Now let's look at gamma 0 squared. Well, this is just beta squared, this is just 1. Let's look at gamma I, gamma j, the commutator of two space-like components. This is beta alpha I, beta alpha j, plus beta alpha j, beta alpha I. This is equal to beta. Let me just commute these, anti-commute these two, minus beta alpha I, alpha j, and let me just anti-commute these two, plus beta minus alpha j, minus beta alpha j alpha I. So this is equal to beta squared is 1, so this is minus alpha I alpha j. Again here beta squared is 1, so minus alpha j, this is j, alpha j alpha I. Well, this we know is minus Kronecker delta ij, or we can also write it as gij, g being our metric tensor. Since we are using the signature 1 minus 1 minus 1 minus 1, the space components of the matrix tensor is just minus the Kronecker delta ij. And what else we have? So no, here there's a 2. So that we can sum up all these relations saying that gamma mu, gamma nu. Oh, okay, so there, let's also check the gamma I squared. No, this all here, you see, this anti-commutator already contains gamma I squared. So when I and j, they are equal, we get twice, this anti-commutator gives us twice gamma I squared is minus 2, so gamma I squared is minus 1. So we can sum up all these by saying that gamma mu, gamma nu is equal to twice g mu nu. And the Dirac equation is again p slash minus m. Let me use the follow the convention and just denote these fields by psi. This is equal to 0, where this psi notation is p mu, gamma mu. Now this gamma matrices, we didn't specify their form, but for most unless we want to interpret physically what this psi, various components of this psi are, we won't really be needing the explicit form of this p, and we will avoid using explicit form of these gamma mu's, as much as possible. So this is our Dirac equation, where the gamma matrices are matrices that satisfy this equation, and p slash is given by defined as the contraction of the 4 vector p and gamma.